All right, today we're going to dive into a really cool machine learning technique called spectral clustering. Now, this one's a bit different. It doesn't find patterns based on how close things are, but on how connected they are. It's a subtle difference, but it changes everything. Let's see how it works.
So when you think about grouping data, your first instinct is probably distance, right? Things that are close together, they belong together. Simple. But what happens when your data doesn't form nice, neat little blobs? What if it's shaped like, say, two intertwined crescent moons or a couple of rings? Yeah, a lot of standard methods get totally lost. And that's exactly where spectral clustering comes in. It's built for these kinds of tricky situations.
Okay, take a look at this. On the left, you've got this big jumble of connected points. The groups are in there, but they're completely hidden. Then look at the right. Bam! Those same points are now perfectly separated into two clean, distinct clusters. The big challenge, the whole point of this, is figuring out how to teach a computer to get from that messy picture on the left to the clear insight on the right, using only the connections between the points. So yeah, that's the central puzzle right there. How do you teach a machine to see these groups? Not based on distance, but on the pathways of connections that link them together. It's a completely different way of looking at the problem, and it needs a totally different approach. All right, to really get a gut feeling for how this works, we're going to borrow a really clever idea from physics, a mass spring system. Trust me, this is going to make all the complicated math behind this feel way more intuitive and hands-on. Just imagine this for a second. Every single one of your data points is a little middle ball, a mass. And the similarity between any two of those points, well, that's a spring connecting them. So if two points are super similar, they get a really strong, stiff spring pulling them together. But if they're not very similar, they get a weak, flimsy spring, or maybe no spring at all. You can almost picture it, right? Now, to actually do anything with this system, we need a way to describe it with numbers. And that's where something called the graph Laplacian comes in. Don't let the name scare you. It's basically just the blueprint for our entire spring system. It's a big grid, a matrix, that tells the computer exactly how strong every single spring is and which masses it connects. It's the master plan.
Okay, so you have this whole system of masses and springs. What if you gave it a little shake? It would start to vibrate, right? But it wouldn't just vibrate randomly. It would move in these very specific, natural wobble patterns. The fancy term for these patterns is eigenvectors. And here's the absolute key insight. The slowest wobbles, the really low-frequency vibrations, are the ones that reveal the weakest spots in the whole network. You'll see the loosely connected groups naturally pull apart and wobble against the more tightly packed clusters. That's where we find our groups.
So, that's the physical intuition, the big idea. It's pretty cool, right? Now let's get down to business and translate that into an actual recipe, a step-by-step algorithm that we can use. It really just boils down to four main steps. Step 1, you build that similarity map, that graph Laplacian we were just talking about. Step 2, you find those fundamental wobble patterns by calculating the first few eigenvectors of that matrix. Now, step 3 is where the real magic happens. You use those eigenvectors to create a brand new way of looking at your data. And finally, step 4, you take this new transformed data and just feed it into a simple clustering method like k-means to find your final groups. Easy as that. So I just mentioned k-means, and you might think it's just the cleanup crew at the end. But it turns out the connection is way deeper than that. Spectral clustering isn't just using k-means. In a really fascinating way, it's kind of like a superpowered version of it. Yeah, the formal connection is laid out perfectly here. The source material says that spectral clustering can be viewed as performing kernel k-means in the eigenspace defined by the graph Laplacian. Okay, I know, that sounds like a mouthful. It's pretty technical, but the idea behind it is actually simple and really, really powerful. Let me break it down. Here's what it really means in plain English. Spectral clustering does all the heavy lifting up front. It takes a really hard problem, where the groups are all twisted and weirdly shaped, and it completely transforms the data. It projects it into this new space where those messy groups suddenly look like simple, easy-to-separate blobs. Then it just calls in an algorithm like k-means to do the easy final step of just drawing circles around them. It turns a hard problem into an easy one. So you might be wondering, why go through all this trouble, all this talk of Laplacians and eigenvectors and wobble patterns? What's the big payoff? Well, it all comes down to the method's unique focus on connectivity, and that focus unlocks some seriously incredible abilities. Because it cares about connections, it can find those weird non-convex shapes we talked about, crescents, rings, spirals, the stuff that just totally stumps other algorithms. It's also a powerhouse for things like image segmentation. Why? Because the pixels that make up a person in a photo, for example, are connected to each other. They're not just a simple blob in space. At the end of the day, it works because it values the path between points more than the straight line distance. And that's a super powerful idea that shows up all over advanced data science. So if there's one thing to take away from all this, it's this. By changing our perspective and viewing data as a network of connections, we can find incredible structures that traditional distance-based methods would just completely miss. And that really leaves us with a final, pretty exciting question, doesn't it? What other hidden structures are out there waiting to be discovered? What hidden communities in our social networks or what crucial protein interactions in biology could this powerful method reveal to us next?